Introduction to GHASH. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving deep into GHASH, which is the authentication function at the heart of GCM mode. Many people understand the encryption part of GCM, which is just CTR mode, but the authentication part using GHASH can be confusing. This presentation is dedicated entirely to understanding exactly how GHASH computes the authentication tag step by step. G-hash stands for galois hash, and it is what makes GCM an authenticated encryption mode. While CTR mode provides confidentiality by encrypting the data, G-hash provides integrity and authenticity by creating a mathematical fingerprint of the data. If even one bit changes, the authentication tag will be completely different, allowing us to detect any tampering. By the end of this presentation, you will understand exactly how GHASH processes data, how it uses Galois field multiplication, how the accumulator works, and how all the pieces come together to create the final authentication tag. We will work through multiple concrete examples with real numbers so there is no ambiguity. GHASH overview and purpose. Before we dive into the mechanics, let us understand what G-hash does at a high level. G-hash is a universal hash function that takes variable length input and produces a fixed 128-bit output. The key property is that it is keyed, meaning you need a secret key H to compute the hash, and without H, you cannot create valid hashes. The inputs to GHASH are the additional authenticated data, which is abbreviated AAD, and the ciphertext from the CTR mode encryption. Both of these need to be authenticated to ensure they haven't been tampered with. The AAD is data that you want to authenticate but not encrypt, for example, packet headers. The ciphertext is the encrypted payload that also needs authentication. G-hash processes the data in 128-bit blocks. If your data isn't a perfect multiple of 128 bits, it gets padded with zeros. Each block is multiplied by the authentication key H in the Galois field GF2 to the power of 128, and the results are accumulated using XOR. This accumulation process is what makes G-hash efficient and allows it to process data incrementally. The output of GHASH is a 128-bit value that represents the accumulated authentication of all the input data. However, this output isn't used directly as the authentication tag. Instead, it's XO-read with an encrypted counter block to produce the final tag. This extra step is crucial for security because it prevents certain attacks on the raw GHASH output. The beauty of G-hash is that it is fast, it can be parallelized, and it provides strong authentication guarantees. The Galois field multiplication might sound complex, but modern processors have hardware instructions that make it extremely fast. This is why GCM with G-hash is the preferred authenticated encryption mode in high-performance applications. The authentication key H. Let's start with the authentication key H, because everything in G-hash revolves around this value. The authentication key H is derived from your AES encryption key using a very simple process. You encrypt a block of all zeros using AES with your key. The resulting 128-bit ciphertext is your H value. So if your AES key is my secret key 12345, you create a 128-bit block of all zeros, beginning with 0x00 ending with 00. You encrypt this using AES with your key, and let's say the output is beginning with 0x66 ending with 2e. This becomes your authentication key H. This H value is fixed for a given encryption key and is used for all GHASH computations with that key. Why do we derive H this way? Because it ensures that H is cryptographically related to the encryption key, but also looks random. An attacker who doesn't know your AES key can't compute H, and even if they could guess the plaintext and ciphertext, they still can't determine H without breaking AES itself. The H value is used in every single Galois field multiplication during G-hash. Every block of data that gets authenticated is multiplied by H. This is what ties the authentication to your secret key. Without knowing H, an attacker cannot compute valid authentication tags, even if they know everything else about the algorithm. It is important to understand that H is not the same as your AES key. Your AES key remains secret and is used for both encryption and for deriving H, but H itself is a derived value that is used specifically for the authentication computations. You compute H once when you set up your encryption, and then you reuse it for all subsequent GHASH operations with that key. GHASH structure and formula. Now let's look at the mathematical structure of G-hash. Don't worry if you're not comfortable with math. I'm going to explain everything step by step in plain language, then show you the mathematical notation, and then work through concrete examples with actual numbers so you can see exactly what's happening. GHASH is basically a recipe that takes your data blocks and mixes them together in a special way using a secret ingredient called H. Think of it like making a smoothie. You start with an empty blender. Then you add ingredients one at a time, blending after each addition. The final smoothie is your authentication tag. Here's the process in plain English. You start with a value called the accumulator, which begins at 0. This is like your empty blender. For each block of data, you do two operations. First, you XOR the block with your current accumulator value. XOR is just a simple operation where you compare bits and keep the ones that are different. Second, you multiply the result by your secret key H using special Galois field multiplication. This becomes your new accumulator value. You repeat this for every block of data. Let me write this in mathematical notation, but I will explain each symbol. We use Y to represent our accumulator value. Y0 is where we start, and it equals 0. The subscript is just a counter. Y0 is the starting value. Y1 is after processing one block, Y2 is after two blocks, and so on. For each block xi, where I is just a number like 1, 2, 3, we compute yi equals yi minus 1 XOR xi, then multiply by h. The XOR operation is shown with a special plus sign in a circle. The Galois multiplication is shown with a different symbol, a dot in a circle. Let me trace through this with very simple numbers. Imagine we have two blocks of data. Start with y0 equals 0. This is our empty accumulator. Now process the first block x1. We compute y1 equals y0 XOR x1 times h, since y0 is 0. XO ring with 0 just gives us x1. So y1 equals x1 times h. This is like putting the first ingredient in the blender and blending it. Now process the second block x2. We compute y2 equals y1 XOR x2 times h. We already know y1 equals x1 times h, so this becomes x1 times h XOR x2 times h. Notice something interesting. The first block x1 gets multiplied by h twice because we multiply when processing x1, then multiply the whole accumulator again when processing x2. This creates a strong relationship between all the blocks. Changing any block changes everything that comes after it. This accumulation is what makes GHASH secure. Every block affects the final result through multiple layers of XOR and multiplication. It is like a chain reaction where changing any link affects the entire chain. An attacker cannot modify one block without changing the authentication tag in an unpredictable way. Understanding XOR, the basics. Before we dive deeper into GHASH, let's make sure we understand XOR, because it's used everywhere in the computation. XOR stands for exclusive OR, and it's a simple operation that works on individual bits. Don't worry, it's much simpler than it sounds. XOR compares two bits and follows this rule. If the bits are different, the result is 1. If the bits are the same, the result is 0. That's it. Let me show you all 4 possible cases. If you XOR 0 with 0, the result is 0, because the bits are the same. If you XOR 0 with 1, the result is 1, because the bits are different. If you XOR 1 with 0, the result is 1, because the bits are different. If you XOR 1 with 1, the result is 0, because the bits are the same. Let's see a concrete example with bigger numbers. Suppose we want to XOR the byte beginning with 0x ending with AB with the byte beginning with 0x ending with 3C first. We convert each byte to binary. Beginning with 0x ending with AB in binary is beginning with 10 ending with 11, and beginning with 0x ending with 3C in binary is beginning with 00 ending with 00. Now we XOR them bit by bit, comparing each position. Starting from the left, 1 XOR 0 equals 1. Next position, 0 XOR 0 equals 0. Next, 1 XOR 1 equals 0. Next, 0 XOR 1 equals 1. Next, 1 XOR 1 equals 0. Next, 0 XOR 1 equals 1. Next, 1 XOR 0 equals 1. Last position, 1 XOR 0 equals 1. So, beginning with 10 ending with 11 XOR beginning with 00 ending with 10 equals beginning with 10 ending with 11, which is 0x97 in hexadecimal. Here is a useful property of XOR. If you XOR anything with 0, you get the original value back. For example, 0xAB XOR 0x00 equals 0xAB. This is why in GHASH, when we start with y0 equals 0 and compute y0 XOR x1, we just get x1. Another useful property. XOR is reversible. If A XOR B equals C, then C XOR B equals A. This is like addition and subtraction being opposites. In GHASH, we use XOR to combine the accumulator with each new data block before multiplying by age. The XOR operation mixes the bits together in a way that is fast to compute and has nice mathematical properties for cryptography. Understanding polynomials, the basics. Now, let's understand polynomials, because Galois field multiplication is based on polynomial math. If you remember algebra from school, you might have seen polynomials, but let me explain them from scratch so everyone is on the same page. A polynomial is an expression made up of terms with variables raised to different powers. For example, x squared plus 3x plus 2 is a polynomial. It has 3 terms. X squared, which is x to the power of 2, 3x, which is 3 times x to the power of 1, and 2, which is the constant term, or x to the power of 0. These powers are also called degrees, so x squared has degree 2. In normal polynomial math, you can add, subtract, and multiply polynomials using rules you learned in algebra. For example, if you multiply x plus 1 times x plus 2, you use the distributive property. X times x equals x squared. X times 2 equals 2x. 1 times x equals x, and 1 times 2 equals 2. Adding them all up, x squared plus 2x plus x plus 2, which simplifies to x squared plus 3x plus 2. In GHASH, we use a special kind of polynomial where the coefficients, the numbers in front of x, can only be 0 or 1. This is called a binary polynomial. For example, x cubed plus x plus 1 is a binary polynomial. It means the coefficient of x cubed is 1. The coefficient of x squared is 0, missing term, the coefficient of x is 1, and the constant is 1. Here is where it connects to our bit strings. We can represent any sequence of bits as a binary polynomial. The bit pattern 1011 represents the polynomial x cubed plus x plus 1. How? Reading from left to right, the first bit, 1, represents x cubed. The second bit, 0, means no x squared term. The third bit, 1, represents x, and the fourth bit, 1, represents the constant term 1. So when we talk about multiplying two 128-bit numbers in the Galois field, we're really multiplying two polynomials where each bit position represents whether that power of x is present or not. A 128-bit number represents a polynomial of degree up to 127, because you have positions for x to the 0, x to the 1, all the way up to x to the 127. Polynomial multiplication in Galois fields. Now let's see how we multiply polynomials in the Galois field used by g-hash. This is different from normal polynomial multiplication, but I'll show you the differences step by step with a simple example. Let's multiply two small binary polynomials. X squared plus 1 times x plus 1. In normal math, we'd use the distributive property. X squared times x equals x cubed. X squared times 1 equals x squared. 1 times x equals x. 1 times 1 equals 1. Adding them. X cubed plus x squared plus x plus 1. But in Galois field arithmetic, we do something different when we add the terms. In Galois fields with binary coefficients, addition is actually XOR, not normal addition. Remember XOR. Same bits give 0, different bits give 1. So when we collect our terms, if a power of x appears an odd number of times, it stays. If it appears an even number of times, it cancels out to 0. In our example, each term appears once, so we get x cubed plus x squared plus x plus 1, which happens to be the same as normal multiplication in this case. Let's try an example where it matters. Multiply x plus 1 times x plus 1. Normal math. X times x equals x squared. X times 1 equals x. 1 times x equals x. 1 times 1 equals 1. We get x squared plus x plus x plus 1. In normal math, that's x squared plus 2x plus 1. But in Galois field arithmetic, the two x terms XOR together. X XOR x equals 0. Same thing XOR s to 0. So we get x squared plus 1. The x term disappeared. Let me show you with actual bit patterns. The polynomial x plus 1 forms the bit pattern 1 1. Reading from left to right, the first one represents x, and the second one represents the constant. Next, we multiply 1 1 by 1 1. This results in x squared plus x plus 1. After performing an XOR operation, this simplifies to x squared plus 1, which is the bit pattern 1 0 1. You can verify this. 1 1 in binary is 3 in decimal. We are computing 3 times 3 in the Galois field, which yields 101 in binary, equivalent to 5 in decimal. Notice that this is not 9, unlike normal multiplication. This carry-less multiplication is what makes Galois field arithmetic special. There's no carrying of bits like in normal multiplication. Each bit position is independent. This property is what allows the PCLMULQDQ instruction on modern CPUs to compute it so quickly. The reduction step keeping results small. When we multiply two 128-bit polynomials, the result can be up to 255 bits long. That's too big. We need to reduce it back to 128 bits. This is where the irreducible polynomial comes in. Let me explain this step by step without assuming any prior knowledge. Think of it like clock arithmetic. On a 12-hour clock, if it's 10 o'clock and you add 5 hours, you don't get 15 o'clock, you get 3 o'clock. You wrap around by subtracting 12. We're doing something similar with polynomials. We wrap around by dividing by a special polynomial and keeping only the remainder. In GHASH, the special polynomial we use is x to the 128 plus x to the 7 plus x to the 2 plus x plus 1. This is called an irreducible polynomial, which means you cannot factor it into simpler polynomials, like how 7 is a prime number that cannot be factored. Let us write this in bits. It is a 1 in position 128, a 1 in position 7, a 1 in position 2, a 1 in position 1, and a 1 in position 0, with zeros everywhere else. When we divide our 255-bit result by this irreducible polynomial, we use polynomial long division just like you learned in school, but with XOR instead of subtraction. The remainder from this division is always less than 128 bits, and that's our final result. The remainder is what we keep. The quotient is thrown away. Let me give you a simple analogy. Imagine we are doing arithmetic modulo 10, which gives us the last digit. If we multiply 7 times 8, we get 56. Then we divide 56 by 10. The quotient is 5, and the remainder is 6. We keep the remainder 6 and throw away the quotient 5. In Galois field arithmetic, we are doing the same thing with polynomials instead of numbers. The specific irreducible polynomial we use in GCM was chosen carefully. It has nice mathematical properties that make the multiplication secure and efficient. The positions of the 1 bits, 1, 2, 8, 7, 2, 1, 0, are not random. They are chosen so that the reduction can be computed quickly with just a few XOR and shift operations after the PCLMULQDQ instruction does the polynomial multiplication. You do not need to do this reduction by hand. The crypto library does it for you. But understanding that it is happening helps you understand why Galois field multiplication is different from normal multiplication, and why it has the security properties that make GHASH work. Complete Galois multiplication example. Let's walk through a complete example of Galois field multiplication from start to finish, using small 4-bit numbers so you can follow every step. The exact same process applies to the 128-bit multiplication in GHASH, just with bigger numbers. We'll multiply 1011 times 1101 in a 4-bit Galois field. First, convert these bit patterns to polynomials. 1011 means x cubed plus x plus 1. When reading from left to right, this means position 3 has a 1, position 2 has a 0, position 1 has a 1, and position 0 has a 1. Similarly, 1101 means x cubed plus x squared plus 1. Step 1 is polynomial multiplication. We multiply x cubed plus x plus 1 times x cubed plus x squared plus 1, using the distributive property. Let me multiply each term. X cubed times x cubed equals x to the 6. X cubed times x squared equals x to the 5. X cubed times 1 equals x cubed. Then x times x cubed equals x to the 4. X times x squared equals x cubed. X times 1 equals x. Finally, 1 times x cubed equals x cubed. 1 times x squared equals x squared, and 1 times 1 equals 1. Now let's collect the terms using XOR for addition. We have x to the 6, appears once, x to the 5, appears once, x to the 4, appears once, x cubed, appears 3 times, x squared, appears twice, x, appears once, and 1 appears once. Remember, in XOR addition, terms appearing an even number of times cancel out to 0. So x squared appears twice and cancels. X cubed appears 3 times. 1 XOR 1 XOR 1 equals 1, so x cubed stays. Our result is x to the 6 plus x to the 5 plus x to the 4 plus x cubed plus x plus 1. Converting back to bits, that's 111011, which is a 7-bit result. We started with 4-bit numbers and got a 7-bit result. Now, we need to reduce this to 4 bits using our irreducible polynomial. For 4-bit fields, let's use x to the 4 plus x plus 1, which, in bits, is 10011. We divide the number beginning with 11, ending with 11, by 10011, using polynomial long division with XOR first. Align 10011 under the leftmost one of the number beginning with 11, ending with 11. Then, XOR them. beginning with 1 1, ending with 1 1 XOR beginning with 1 0, ending with 0 0. This second number, beginning with 1 0, ending with 0 0, is 1 0 0 1 1 shifted left 2 positions. The result equals beginning with 0 1, ending with 1 1. Next, align 1 0 0 1 1 under the leftmost one of beginning with 0 1, ending with 1 1. Now, XOR them. Beginning with 0 1, ending with 1 1 XOR beginning with 0 1, ending with 1 0. This second number, beginning with 0 1, ending with 1 0, is 1 0 0 1 1 shifted left 1 position. The result equals beginning with 0 0, ending with 0 1. Finally, XOR beginning with 0 0, ending with 0 1 with beginning with 0 0, ending with 1 1. This third number, beginning with 0 0, ending with 1 1, is 1 0 0 1 1 not shifted. The final result equals beginning with 0 0, ending with 1 0. The remainder is 0 0 1 0, which is 2 in decimal. So 1011 times 1101 in this 4-bit Galois field equals 0010. That's our final answer. In 128-bit GHASH, the process is identical but with 128-bit numbers and the 128-bit irreducible polynomial. The PCLMULQDQ instruction does the multiplication part, and a few XOR and shift operations do the reduction. Processing additional authenticated data. Let's walk through how GHASH processes the additional authenticated data, or AAD. The AAD is the first input to GHASH, processed before the ciphertext. If you don't have any AAD, you simply skip this step and start with the ciphertext. First, you break the AAD into 128-bit blocks. If your AAD is not a multiple of 128 bits, you pad it with zeros to make the last block complete. For example, if your AAD is header 123, which is 9 bytes or 72 bits, you add 56 0 bits to make it 128 bits total. Let's say your AAD padding results in blocks A1, A2, up to AA, where A is the number of AAD blocks. You process these blocks through the GHASH formula. Start with Y0 equals 0. Compute Y1 as the result of Y0 XOR A1, then multiply that by H. This ultimately equals A1 times H. Next, Y2 is calculated as Y1 XOR A2, then multiplied by H. Continue this process until YA is the result of YA minus 1 XOR AA, then multiplied by H after processing all AAD blocks. YA is your intermediate accumulator value. Let's do a concrete example. Suppose your AAD is a single 128-bit block with value beginning with 1 1 ending with 1 1, and your H is beginning with AA ending with A. Start with Y0 equals 0. Compute Y1 equals 0 XOR beginning with 1 1 ending with 1 1 times beginning with AA ending with AA. The XOR with 0 just gives beginning with 1 1 ending with 1 1. Now you multiply this by H in the Galois field to get Y1. Let's say the Galois multiplication gives you beginning with 2 2 ending with 2 2. This Y1 is your accumulator after processing the AAD. The key insight is that the AAD processing is just the first part of GHASH. The accumulator value after processing AAD becomes the starting point for processing the ciphertext. This is how GHASH combines authentication of both AAD and ciphertext into a single output. Processing ciphertext. After processing the AAD, GHASH continues by processing the ciphertext. The ciphertext is also broken into 128-bit blocks, with 0 padding on the last block if necessary. Let's call these blocks C1, C2, up to CC, where C is the number of ciphertext blocks. The processing continues from where AAD left off. If you had an AAD blocks, your accumulator is YA. Now, you process the first ciphertext block. Y parenthesis a plus 1 parenthesis equals parenthesis ya XORC 1 parenthesis times H, then Y parenthesis a plus 2 parenthesis equals parenthesis Y parenthesis a plus 1 parenthesis XORC 2 parenthesis times H. You continue until you have processed all C ciphertext blocks, ending with Y parenthesis a plus C parenthesis. Let's continue our previous example. After processing AAD, we had Y1 equals beginning with 0x22, ending with 22. Now suppose our ciphertext is a single 128-bit block C1 with value beginning with 0x33, ending with 33. We compute Y2 as Y1 XOR C1 times H, that's the value beginning with 0x22, ending with 22, XOR the value beginning with 0x33, ending with 33, all times H. The XOR gives beginning with 0x11, ending with 11. Wait, let me recalculate that. 0x22 XOR 0x33, in binary, is beginning with 00, ending with 10, XOR beginning with 00, ending with 11. This equals beginning with 00, ending with 01, which is 0x11. So the XOR gives beginning with 0x11, ending with 11. Now multiply by H in the Galois field to get Y2. Let's say that's beginning with 0x44, ending with 44. Notice that both AAD and ciphertext are processed the same way. XOR with the accumulator, then multiply by H. The G-hash function does not distinguish between AAD and ciphertext in terms of how it processes them. They are just a sequence of blocks that get fed through the same iterative formula. After processing all AAD and ciphertext blocks, you have an accumulator value YA plus C that represents the authentication of all that data. But we are not done yet. There is one more crucial step: the lengths block. The lengths block. The lengths block is a special 128-bit block that GHASH processes after all the AAD and ciphertext blocks. This block contains the bit lengths of the AAD and ciphertext and is critical for security. Without the lengths block, certain attacks would be possible, allowing an attacker to manipulate the boundaries between AAD and ciphertext. The lengths block is structured as follows. The first 64 bits contain the length of the AAD in bits, and the second 64 bits contain the length of the ciphertext in bits. Both lengths are represented as 64-bit big Endian integers. For example, if your AAD is 72 bits and your ciphertext is 16 bits, the lengths block is beginning with 0x00 and ending with 10 in hexadecimal. Let's break that down. 72 in decimal is 0x48 in hexadecimal. As a 64-bit big Endian value, that's 0x, beginning with 00 and ending with 48. Similarly, 16 in decimal is 0x10 in hexadecimal, which as a 64-bit value is 0x, beginning with 00 and ending with 10. Concatenating these gives the full 128-bit length block. This lengths block is processed just like any other block through G-hash. If your accumulator after processing all AAD and ciphertext is Y of a plus C, then you compute Y of a plus C plus 1 equals Y of a plus C XOR lengths block times H. This final multiplication incorporates the lengths into the authentication. Continuing our running example, after processing AAD and ciphertext, we had Y2 equal to 0x44, ending with 44. Our AAD was 128 bits and ciphertext was 128 bits, so the lengths block is 0x00, ending with 80. We compute Y3 equal to Y2 XOR lengths block, multiplied by H. The XOR of 0x44, ending with 44, and 0x00, ending with 80, gives 0x44, ending with C44. The 0x80 changes some of the 0 by 44 bytes. Multiply this by H in the Galois field to get Y3. Let's say the result is 0x55, ending with 55. This Y3 is the final GASH output. Creating the authentication tag. The GHASH output is not used directly as the authentication tag. There is one final step. We XOR the GHASH output with an encrypted counter block. This step is essential for security and ties the authentication to the specific message and IV. Remember, in GCM, we use counter blocks for encryption starting at counter 1. Counter 0 is special and reserved for this authentication step. We take our IV, append a counter value of 0, encrypt this counter block with AES and our key, and the result is our authentication keystream block. Let's say our IV is IV, beginning with 98, ending with 10. And we append counter 0 to make IV, beginning with 98, ending with 10, pipe 000. We encrypt this with AES and our key, producing, for example, 0x77, ending with 77. This is our authentication keystream. Now we XOR the GHASH output with this keystream. In our running example, GHASH output is 0x beginning with 55 ending with 55, and the keystream is 0x beginning with 77 ending with 77. The XOR is 0x beginning with 22 ending with 22. This is our final authentication tag. This tag is what gets sent along with the ciphertext and IV. The receiver will recompute GHASH using the received data, XOR it with their own encrypted counter 0, and compare the result with the received tag. If they match, the authentication passes. If even one bit is different, authentication fails and the message is rejected. The reason for this final XOR is security. The raw G-hash output has certain mathematical properties that could potentially be exploited. By XORing with an encrypted counter block that is unique to this message, we add a layer of protection that makes these attacks impossible. The encrypted counter block is like a one-time pad that masks the G-hash output. Complete GHASH example step by step. Let's work through a complete example from start to finish, with concrete values, so you can see exactly how GASH works. We'll use simplified values to make the arithmetic easy to follow, but the process is identical to real GCM. Setup. The AES key is my secret key 123. The IV is IV beginning with 12 ending with 90. AAD is head which is 32 bits, and the plaintext is OK which is 16 bits. First, we encrypt the plaintext using CTR mode, starting at counter 1, to get the ciphertext. Let's say the ciphertext is 0x beginning with a B ending with CD. Step 1. Generate authentication key H encrypt zeros. H equals AES of beginning with 0x00 ending with 00 and the key, which results in beginning with 0x11 ending with 11. This is simplified. Step 2. Process AAD head is 32 bits, pad to 128 bits. Beginning with 48, ending with 44, followed by 96 0 bits, equals beginning with 48, ending with 00. This is block A1. Compute Y1 equals open parenthesis 0 XOR A1 close parenthesis times H, equals beginning with 48, ending with 00, times beginning with 11, ending with 11. Let's say the galois multiplication gives Y1 equals beginning with 22, ending with 22. Step 3. Process ciphertext. Ciphertext beginning with 0xAB ending with CD is 16 bits, padded to 128 bits. Beginning with 0xAB ending with 00. This is block C1. Compute Y2 equals the quantity Y1 XOR C1 times H, which equals the quantity beginning with 0x22 ending with 22 XOR beginning with 0xAB ending with 00 times H. The XOR gives approximately beginning with 0x22 ending with 22. Multiply by h to get y2 equals beginning with 0x33 ending with 33. Step 4. Process lengths block. AAD is 32 bits. Ciphertext is 16 bits. The lengths block is beginning with 0x00 ending with 10. To compute y3, we take y2 XOR lengths, then multiply the result by h specifically. This means we XOR the value beginning with 0x33 ending with 33 with the value beginning with 0x00 ending with 10, and then multiply that result by h. The XOR operation gives beginning with 0x33 ending with 23. Next, multiply by h to get y3, which equals beginning with 0x44 ending with 44. This is the GHASH output. Step 5. Create tag. First, encrypt counter 0. AES, with IV, beginning with 12 ending with 90, pipe, 000, and the key, equals 0x beginning with 55 ending with 55. The tag is calculated as GHASHXOR the encrypted counter. This equals 0x beginning with 44 ending with 44, XOR 0x beginning with 55 ending with 55, resulting in 0x beginning with 11 ending with 11. This is the final authentication tag sent with the ciphertext. Verification process. Now let's see how the receiver verifies the authentication tag. The receiver has the ciphertext, the IV, the AAD, the tag, and the shared secret key. The receiver computes GHASH independently and checks if their computed tag matches the received tag. Continuing from our previous example, the receiver has ciphertext 0xabcd, IV 1 2 3 4 5 6 7 8 9 0, AAD head, tag 0x11, ending with 11, and key my secret key 123. The receiver performs exactly the same G-hash computation. Step 1. Generate H-encrypt zeros with their key. H equals 0x11, ending with 11. This is the same as the senders, because they use the same key. Step 2. Process received AAD headpads to beginning with 48, ending with 00. Compute Y1 equals A1 times H, which equals beginning with 22, ending with 22. Same as sender. Step 3. Process received ciphertext 0xabcd pads to beginning with 0xab ending with 00. Compute y2 equals open parenthesis y1x or c1 close parenthesis times h equals beginning with 0x33 ending with 33, same as sender. Step 4. Process lengths block. Lengths are 32 bits and 16 bits, giving 0x00, ending with 10. Compute y3 equals y2 XOR lengths times h equals 0x44, ending with 44, same as sender. This is the receiver's GHASH output. Step 5. Compute the tag. Encrypt counter 0 with their IV and key, beginning with 0x55 and ending with 55. The computed tag equals beginning with 0x44 and ending with 44x or beginning with 0x55 and ending with 55 equals beginning with 0x11 and ending with 11. Step 6. Compare. Received tag is beginning with 0x11, ending with 11. Computed tag is beginning with 0x11, ending with 11. They match exactly. Authentication passes. The receiver can now proceed to decrypt the ciphertext, confident that the data has not been tampered with and came from someone with the correct key. If the tags didn't match, even by a single bit, the receiver would reject the entire message without decrypting. This is the power of authenticated encryption. Any tampering is detected before you even touch the plaintext. Why GHASH is secure. Let's understand why GHASH provides strong authentication. The security comes from the combination of the secret key H and the properties of Galois field multiplication. Without knowing H, an attacker cannot compute valid GHASH outputs, and therefore cannot create valid authentication tags. First, H is derived from the AES key by encrypting zeros. To compute H without knowing the key, you would have to break AES, which is considered computationally infeasible. So an attacker who does not have your key does not have H either. Second, even if an attacker somehow learned H, the Galois field multiplication makes it extremely difficult to manipulate the authentication tag in useful ways. Suppose an attacker wants to flip bit 5 of the ciphertext. This changes the ciphertext block, which changes the GHASH computation. But how does it change the final tag? The relationship is complex because of the Galois multiplication and the XOR operations. The attacker would need to solve a system of equations in the Galois field, which is hard. Third, the lengths block prevents certain forgery attacks. Without the lengths block, an attacker might be able to take a valid message with AAD and ciphertext and redistribute bits between them while maintaining a valid tag. The lengths block makes this impossible because it explicitly authenticates the lengths of both fields. Fourth, the final XOR with the encrypted counter block provides additional protection. The raw GHASH output has certain algebraic properties. By masking it with an encrypted counter that is unique to this message, we prevent attacks that might exploit those properties. This is similar to how a one-time pad provides perfect secrecy. The mathematical proof of GCM's security shows that as long as IVs are never reused with the same key, the probability of an attacker successfully forging a valid authentication tag is at most 2 to the power of -128 for a 128-bit tag, which is negligibly small. This makes GCM extremely secure when used correctly. GHASH in parallel processing. One of the advantages of GHASH is its ability to be parallelized. This makes GCM very fast on modern multi-core processors. Let's understand how this parallelization works and why GHASH's structure enables it. At first glance, GHASH looks sequential because each step depends on the previous accumulator value. You compute Y1, then use Y1 to compute Y2, then use Y2 to compute Y3, and so on. However, there is a clever way to parallelize this using the mathematical properties of Galois field multiplication. The key insight is that Galois field multiplication is associative, meaning A times B times C equals A times B times C. This allows us to precompute powers of H and use them to process multiple blocks simultaneously. Instead of computing Y1 equals X1 times H, then Y2 equals Y1 XOR X2 times H sequentially, we can compute them in parallel using powers of H. Here's how. First, precompute H squared, which is H times H cubed, which is H times H times H, and so on. Now, if you have 4 blocks, X1, X2, X3, and X4, you can compute their contributions in parallel. Core 1 computes X1 times H to the 4th. Core 2 computes X2 times H cubed. Core 3 computes X3 times H squared. And Core 4 computes X4 times H. Then, you XOR all 4 results together to get the final accumulator after 4 blocks. This is mathematically equivalent to sequential processing but can be done in parallel. The formula works because G# has the property that Y4 equals the result of starting with Y0 XOR X1, then multiplying by H, then XOR X2, and multiplying by H, then XOR X3, and multiplying by H, then XOR X4, and finally, multiplying by H. This expands to X1 times H to the 4th XOR X2 times H cubed XOR X3 times H squared XOR X4 times H, all of which can be computed independently. In practice, implementations precompute several powers of H when they initialize. Then during GHASH computation, they process blocks in batches using parallel operations. Modern CPUs with vector instructions can compute multiple Galois multiplications simultaneously, making this extremely fast. This is one reason GCM is so popular for high-performance applications. G-hash with empty AAD. A common case in practice is when there's no additional authenticated data, meaning AAD is empty. Let's see how G-hash handles this case, which actually simplifies the computation. When AAD is empty, the AAD length is 0 bits. In the G-hash computation, you simply skip the AAD processing phase entirely and start directly with the ciphertext. Your initial accumulator Y0 is still 0, but your first actual computation is for the first ciphertext block. Let us do an example. Suppose your ciphertext is a single 128-bit block C1 equals 0x12 ending with 9012, and your H is 0xAA ending with AAA start with Y0 equals 0. Since there is no AAD, you go straight to ciphertext. Compute Y1 equals parentheses Y0 XOR C1 parentheses times H equals parentheses 0 XOR 0 x 1 2 3 4 5 6 7 8 and so on parentheses times H equals 0 x 1 2 3 4 5 6 7 8 and so on times H in Galois field. Let us say this gives 0 XBB ending with BBBB. Next, you process the lengths block. AAD length is 0 bits. Ciphertext length is 128 bits. The lengths block is beginning with 0x00 and ending with 80. Compute Y2 equals Y1 XOR lengths times H equals beginning with 0xBB XOR beginning with 0x00 and ending with 80 times H. The XOR gives beginning with 0xBB and ending with 3B. The 0x80 changes the last byte from BB to 3B. Multiply by H to get Y2, let's say beginning with 0xCC and ending with CC. This is your G-hash output. Then you XOR with encrypted counter 0 as usual to get the final tag. The process is exactly the same, just with fewer blocks to process. This makes empty AAD cases faster because there are fewer Galois multiplications to compute. Many applications don't use AAD at all. For example, when encrypting files locally, you might only encrypt the file contents without any additional metadata to authenticate. In such cases, G-hash with empty AAD is perfectly fine and provides authentication of the ciphertext alone. GHASH with empty plaintext. Another edge case is when the plaintext is empty, meaning you are only authenticating AAD without encrypting anything. This is less common but perfectly valid in GCM. Let us see how GHASH handles this. When plaintext is empty, ciphertext is also empty because there is nothing to encrypt. The ciphertext length is 0 bits. In the GHASH computation, you process the AAD blocks normally, then skip the ciphertext phase, and go straight to the lengths block. Example. AAD is metadata which is 64 bits. Padded to 128 bits gives 0x beginning with 4D ending with 00. Your H is 0x beginning with DD ending with DD. Compute Y1 equals 0x or AAD times H equals AAD times H, giving let's say 0x beginning with EE ending with EE. Now, let's process the lengths. The AAD is 64 bits, and the ciphertext is 0 bits. The lengths block is 0x beginning with 00, ending with 00. Compute Y2, which equals Y1 XOR lengths, multiplied by H. This is equivalent to 0xEE ellipsis XOR 0x beginning with 00, ending with 00. Multiplied by H. Let's say this results in 0x beginning with FF, ending with FF. This is the GHASH output. You XOR it with encrypted counter 0 to get the tag as usual. The resulting tag authenticates the AAD, even though there is no ciphertext. This can be useful in protocols where you want to authenticate metadata without encrypting it. An example use case might be authenticating a control message that has a command in the AAD field but no payload. The command needs to be readable but also needs authentication to prevent tampering. GCM with empty plaintext provides exactly this. Multiple block example. Let's work through an example with multiple blocks to see how the accumulator builds up. This will show how Ghash processes longer messages and how each block contributes to the final tag. Setup. AAD is 256 bits, 2 blocks. Ciphertext is 384 bits, 3 blocks. H is beginning with 0x11 ending with 11. Let's denote the blocks as A1. A2 for AAD and C1, C2, C3 for ciphertext. For simplicity, let's say A1 equals 0x11 ending with 11, 32 ones. A2 equals 0x22 ending with 22. C1 equals 0x33 ending with 33. C2 equals 0x44 ending with 44. C3 equals 0x55 ending with 55. Start with Y0 equals 0. Process A1. Y1 equals Y0 XOR A1 times H equals beginning with 0x11 and ending with 11 times H. Let us say galois multiplication gives beginning with 0xAA and ending with A. Process A2. Y2 equals Y1 XOR A2 times H equals beginning with 0xAA and ending with AA XOR beginning with 0x22 and ending with 22 times H equals beginning with 0x88 and ending with 88 times H, giving let us say beginning with 0xBB and ending with BB. We have finished AAD processing. Process C1. Y3 equals Y2 XOR C1 times H equals beginning with 0xBB ending with BB XOR beginning with 0x33 ending with 33 times H equals beginning with 0x88 ending with 88 times H, giving beginning with 0xCC ending with CC. Process C2. Y4 equals Y3 XOR C2 times H equals beginning with 0xCC ending with CC XOR beginning with 0x44 ending with 44 times H equals beginning with 0x88 ending with 88 times H, giving beginning with 0xDD ending with DD. Process C3. Y5 equals Y4 XOR C3 times H equals beginning with 0xDD ending with DD XOR beginning with 0x55 ending with 55 times H equals beginning with 0x88 ending with 88 times H, giving beginning with 0xEE ending with EE. We've finished ciphertext processing. Process lengths. AAD is 256 bits. Ciphertext is 384 bits. Lengths block is beginning with 0x00 ending with 180. Y6 equals Y5 XOR lengths times H equals beginning with 0xEE ending with EE XOR beginning with 0x00 ending with 180 times H, giving final GHASH output let's say beginning with 0xFF ending with FF. XOR with encrypted counter 0. Let's say beginning with 0x99 ending with 99. To get the final tag beginning with 0x66 ending with 66. This tag authenticates all 2 AAD blocks and 3 ciphertext blocks. Notice how the accumulator Y evolved through 6 steps, incorporating each block's contribution through the galois multiplication. Impact of bit changes on GHASH. Let's examine what occurs when you change a single bit in the input and observe its effect on the Ghash output. This demonstrates the avalanche effect that makes Ghash a strong authentication function. Start with a simple example. A single ciphertext block C equals beginning with 0x00 ending with 00. H equals beginning with 0x11 ending with 11. No AAD compute GHASH. Y1 equals 0 XORC times H equals 0 times H equals 0. Process lengths. Ciphertext 128 bits. Y2 equals 0 XOR beginning with 0x00 ending with 80 times H. Let's say this gives beginning with 0x22 ending with 22. XOR with encrypted counter 0. Let's say beginning with 0x99 ending with 99. To get tag beginning with 0xBB ending with BB. Now flip one bit in the ciphertext. Change C to 0x, beginning with 00 ending with 01. This flips the last bit. To recompute, Y1 equals 0 XOR 0x, beginning with 00 ending with 01, times H. This then equals 0x, beginning with 00 ending with 01, times H. This galois multiplication yields a completely different result. For example, 0x, beginning with 33 ending with 33. To process the lengths, Y2 equals 0x, beginning with 33, XOR 0x, beginning with 00 ending with 80, times H. This results in, for example, 0x, beginning with 44 ending with 44. XOR this with the same encrypted counter, 0x, beginning with 99, to get the tag 0x, beginning with DD ending with DD. Compare. Original tag beginning with 0xBB and ending with BB versus modified tag beginning with 0xDD and ending with DD. Flipping one input bit changed many output bits. This is the avalanche effect. The galois field multiplication ensures that small input changes cause large, unpredictable output changes. This property is crucial for security. An attacker who flips bits in the ciphertext cannot predict what the new tag should be. Without knowing H, they cannot compute the correct tag for the modified ciphertext. When the receiver recomputes the tag, it will not match the original tag, and authentication fails, thus detecting the tampering. GHASH versus other hash functions. Let's compare ghash to other hash functions to understand what makes it special, and why it's used in GCM. Ghash is different from cryptographic hash functions like SHA-256 in several important ways. First, ghash is keyed, meaning you need a secret key H to compute it. SHA-256 and similar functions are unkeyed. Anyone can compute them on any input. This makes ghash suitable for authentication because only someone with the key can create valid outputs. Unkeyed hashes cannot provide authentication without additional mechanisms like HMAC. Second, ghash is a universal hash function, which is a special class of hash function with specific mathematical properties. Universal hash functions guarantee that for random keys, the collision probability is low. This is weaker than cryptographic hashes, which must resist collision attacks even when the attacker chooses the inputs carefully. But for authentication, the universal hash property combined with a secret key is sufficient. Third, ghash is extremely fast, especially with hardware support. On modern CPUs with AES-NI and PCLMULQDQ instructions, ghash can process data at multiple gigabytes per second. SHA-256 is slower, even with hardware acceleration. This speed makes ghash ideal for high-throughput applications like network encryption. Fourth, ghash has a special algebraic structure based on galois field arithmetic. This structure enables parallelization and incremental computation in ways that SHA-256 cannot match. You can process multiple ghash blocks in parallel on different CPU cores, while SHA-256's Merkle-Damgard structure is inherently sequential. However, ghash is not a general-purpose hash function. You would not use ghash for things like password hashing or content addressing where SHA-256 excels. Gash is specifically designed for authenticated encryption in modes like GCM, and it is optimized for that use case. Common implementation mistakes. Let's discuss common mistakes developers make when implementing GHASH and how to avoid them. Understanding these pitfalls helps ensure correct and secure implementation. Mistake 1. Using byte lengths instead of bit lengths in the lengths block. The lengths must be in bits, not bytes. If your AAD is 16 bytes, the length is 128 bits, which is beginning with 0x00 ending with 80, not beginning with 0x00 ending with 10. This mistake causes authentication to fail even with correct data. Mistake number 2 is incorrect byte ordering in the lengths block. The lengths are 64-bit big Endian integers. On Little Endian systems, you need to swap the bytes. If you write the length value directly from memory without conversion, you will get the wrong value in the lengths block. Mistake 3. Not padding blocks correctly. All blocks must be exactly 128 bits. If your last AAD or ciphertext block is shorter, you must pad with zeros on the right. Padding on the left or using non-zero padding values will give wrong results. Mistake 4. Incorrect galois field multiplication implementation. The multiplication must use the correct irreducible polynomial x to the 128 plus x to the 7 plus x to the 2 plus x plus 1. Using the wrong polynomial or implementing the reduction incorrectly gives wrong results. Always use tested library implementations rather than writing your own galois multiplication. Mistake 5. Forgetting to process the lengths block. Some implementations mistakenly think G-hash is just AAD and ciphertext processing. The lengths block is mandatory and must always be processed, even if AAD or ciphertext is empty. Mistake 6. Using the wrong counter for the final XOR. The encrypted counter must be counter 0 with the message's IV, not counter 1 or any other value. Using the wrong counter gives a different tag that won't verify. Mistake number 7. Not using constant time comparison for tag verification. When comparing the computed tag with the received tag, use constant time comparison to prevent timing attacks. A simple byte-by-byte comparison that exits early on mismatch can leak information about which bytes match. GHASH performance optimization. Let's discuss how to optimize G-hash performance. Understanding these optimizations helps you make informed decisions when implementing or configuring GCM. First, use hardware acceleration. Modern Intel and AMD CPUs feature the PCLMULQDQ instruction. This instruction is specifically for carry-less multiplication, which is used in galois fields. This makes galois multiplication extremely fast. Use crypto libraries that detect and use this instruction when it is available. The performance difference between software and hardware implementation can be 10x or more. Second, precompute powers of h instead of computing h times h during operation. Precompute h squared, h cubed, and so on up to some limit during initialization. Store these in a table. During GHASH computation, use these precomputed powers to parallelize block processing as we discussed earlier. The memory cost is small compared to the performance benefit. Third, process data in larger batches. Instead of computing G-hash for one block at a time, accumulate several blocks and process them together using the parallel technique with precomputed powers. This reduces function call overhead and allows better utilization of CPU pipelines and vector instructions. Fourth, align your data to cache line boundaries. Modern CPUs perform better when data is aligned. If your blocks are aligned to 16-byte boundaries, the CPU can load them more efficiently. This is a small optimization, but it can add up in high-throughput scenarios. Fifth, use vectorized implementations. SIMD instructions, like SSE, AVX, or NEON, can process multiple operations simultaneously. Some libraries provide vectorized GHASH implementations that use these instructions to process several blocks in parallel on a single core. Sixth, minimize data copies. If possible, compute G-hash directly on the data where it lives rather than copying it to a temporary buffer. Every memory copy costs time, especially for large messages. Design your APIs to allow in-place G-hash computation. Summary and conclusion. Let's recap everything we've learned about G-hash and how it computes. The authentication tag in GCM. G-hash is a keyed universal hash function that provides authentication for both additional authenticated data and ciphertext in GCM mode. The core of GHASH is an iterative process that maintains an accumulator value. Starting from 0, for each 128-bit block, you XOR the block with the current accumulator and multiply by the authentication key H in the galois field GF2 to the power of 128. This process incorporates each block's contribution into the accumulator. G-hash processes data in 3 phases. First, the AAD blocks, then the ciphertext blocks, then a special lengths block containing the bit lengths of AAD and ciphertext. Each phase uses the same XOR then multiply operation, building up the accumulator progressively. The authentication key H is derived by encrypting a block of zeros with the AES key. This ties the authentication to the same secret key used for encryption. The final step XORs the GHASH output with an encrypted counter block, producing the authentication tag that gets sent with the message. The security of GHASH comes from the secret key H and the properties of galois field multiplication. Without knowing H, an attacker cannot compute valid tags. The galois multiplication ensures that changing any input bit changes the output unpredictably, making forgery extremely difficult. GHASH is fast, especially with hardware support, and can be parallelized for even better performance. Its design makes GCM one of the fastest authenticated encryption modes available, which is why it is widely used in TLS, IPsec, and other high-performance security protocols. Thank you for your attendance. Please consider subscribing to the channel.